Hello, and welcome to this video on energy analysis in resistance welds. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com, and you are watching this video on my YouTube channel, The Weld Nugget. So today we're going to look at energy analysis of resistance spot welds. Now, I had presented a similar video on analysis of laser welds, and that is already on my YouTube channel. For those who are not familiar with resistance welding, I have a resistance welding playlist, and there are many videos on that as well. The resistance weld, as shown as a schematic in terms of the equipment, is made of a controller and a transformer. In some situations, the controller and transformer are in a single unit, so you might not actually physically see those two as separate. The controller is where you control the time, and you also control the input current and voltage depending on the control modes. The energy goes from the controller through a transformer where it is changed from high voltage low current to a low voltage high current signal, which goes into the secondary. And this high current signal, high current pulse goes through the electrodes, through the parts being welded, back into the bottom electrode and comes back to the transformer. We can measure the voltage across the secondary close to the electrodes, usually on the electrode holder, and we get a number for voltage as well. So now we know the time, the current, and voltage, and we can calculate the energy that we put on a single weld. So current times voltage times time, it would be the energy. Current times voltage is power, and power times time would be energy. And we get the energy number in joules if we have the right units. Now, what exactly happens when you make a weld between two parts? Here I'm showing you a schematic of two sheets of metal being welded with two electrodes. And we can see that a fusion nugget has formed. A fusion nugget is a volume of metal which actually melted during the weld. And as the weld cools down, the molten metal solidifies. Not all welds produce a fusion nugget. There are resistance welds which produce a solid state bond, but for this type of analysis, it was easier to use samples or examples where you actually form a nugget for doing this analysis. Force is applied by the electrodes, the current flows through the electrodes, and you generate the right amount of heat for the right amount of time to form a nugget which meets specifications. Oftentimes, this nugget is in the form of an ellipsoid. Essentially, it's an ellipse, but in the 3 dimensions, so that's called an ellipsoid. And the molten metal is contained by having the right amount of size of the electrode as well as pressure, so that even though the molten metal is there, it is not able to escape. If it escapes, then you get a lot of flash. So if the process is properly designed, then the molten metal is properly trapped, and as it cools down, it forms that weld. Here we see a spot weld in aluminum. These are two sheets of aluminum. Each one is about 40 thousandths or about 1 millimeter. And this is 2024 clad aluminum. So 2024 is an aerospace alloy, aluminum with small amount of copper. And on the surface, it is coated with pure aluminum for corrosion protection. In this particular weld, the weld was made at 20.8 kiloamps for 60 milliseconds with a voltage of 2 volts measured at the electrode holders. So the energy which was measured, the input energy, is current times time times voltage, and we get a number of 2496 joules. This energy was used to make a fusion nugget, which looks like an ellipsoid, and the volume of the ellipsoid was calculated by this formula is 4 by 3 times pi times A, B, and C. A, B, and C are radii of the ellipse in different directions, and we get a volume. We can do a similar analysis for stainless steels. And here I'm showing you a nugget formed in stainless steel. In this case, the sheet metal was even thinner, about 16 thousandths or say 400 microns. And we needed 6 kiloamps of current for 200 milliseconds of time, 215 milliseconds, and 2.2 volts. And the energy calculated is 2838 joules, and the corresponding volume of ellipse was calculated as well. Now that we know the volume of these nuggets, we can use known numbers for different material properties for these two materials and calculate the energy that would have been required to raise that volume of material from room temperature up to the melting point and then actually melt it. And that can be separated into two. One is the energy required to go from room temperature to the melting point, and the second is energy required to actually fuse. So energy required to heat is given by M times heat capacity times the difference in temperature from melting point to say starting point of 20. And heat of fusion is mass into energy for fusion is mass times heat of fusion. We have these material properties. We know the mass of the metal because now we know the volume and we multiply by density. And now we can calculate the energy required to raise this volume from room temperature to melting point. Of course, we are assuming that we don't go much above melting point. And it is possible that the melt is actually going above melting point, but we don't know by how much. So we are just going to assume it goes up to melting point. It might be going slightly further as well. Then we can do some simple math using the material properties. And we have different inputs over here in terms of mass, density, heat capacity, melting point, heat of fusion for aluminum as well as stainless steel. And we calculate different numbers for melting for aluminum for that nugget and the energy required for melting for stainless steel. The size of the aluminum nugget was much bigger, so we find that the energy required is much bigger for that one compared to stainless steel. We know the input energies, and we divide the energy based divide by the total input energy, and we find that the percent heat used for melting is a very small fraction of the total heat input. So we are providing of the order of 2500 joules, and a very small number is used to create that melt from room temperature to melting point to form that nugget. So where exactly is the rest of the energy going? So obviously we are losing a lot of energy or not properly using that energy. So what we realize is a lot of times, especially when we are making structural welds, we are using electrodes that are cooled with chilled water. So the electrodes are actually hollow and chilled water is flowing through the electrodes. And the electrodes on one hand are providing the energy to make that weld. So we are passing current through the two electrodes, through the parts and back to the other electrode, back to the transformer. At the same time, we also need to uh, take some heat away, in fact, a lot of heat away by chilled water because we want to make sure that the nugget grows but does not grow too much. We don't want the nugget to actually extend all the way to the surface because then it won't meet spec and it will actually start sticking to the electrodes. So we want to grow a nugget, but we don't want to grow a nugget too big. So that requires a lot of cooling. So we are taking a lot of the heat out of the weld. Another way of losing the heat is lost by conduction. So the two parts themselves are sheets. And even though the component might not appear to be big, the weld itself is so tiny that any decent sized component acts like a giant heat sink. So we have the sheet metal itself in two dimensions sucking the heat away from the weld. Another cause for discrepancy can be that the voltage we are measuring is actually not very close to the weld tips because we cannot place the electrodes right at the tip of the resistance welding electrode. So we actually place the electrode voltage pickup leads on the electrode holder. So there's obviously going to be some energy which is required for the current to flow just through that circuit. But that's not going to be substantial because this entire circuit is actually pretty much made of very conductive copper. So some of the energy might be lost in there, but not significant. So most of the energy, what we find is going to be lost is by heat loss by conduction through the electrodes as well as conduction through the parts themselves. Another assumption, as we have mentioned, is we are assuming that we are only going up to the melting point. It is perhaps possible that we are going actually higher than melting point. But even with that, even if it was some number, maybe even 100% more, still the percent used for melting is going to be still a very, very small number. So that tells you that welding and similar, we saw similar results in laser welding, that a very small fraction is used for actually generating the fusion. A lot of the energy is lost for different reasons. In laser welding, the loss was for a different reason. In resistance welding, we are finding the loss is going to be mostly by conduction. So in summary, resistance welds are based on heat generated from resistance to current flow. And in some cases, it does generate a nugget. There are welds where there is no nugget formation, but then such an analysis, and those are actually at a lower temperature, but it would be difficult to do such an analysis in those situations. So in this case, I have used samples where we do form a nugget. And what we have found is only a very small fraction of the absorbed energy is used for melting. The rest is lost primarily by conduction, which is not as a huge surprise, but the efficiency, such a low efficiency came as a surprise to me. I would have thought it would be maybe 5, 10, 20%, but it is a very small number than that. We do find that welding aluminum, since aluminum is very conductive, we have to go in at much higher peak current and much shorter time in order to able to contain the heat enough to create some melt. So the efficiency is better in aluminum because we don't give it enough time for the heat to flow out. Whereas stainless steels, because they are a lot more resistive, you have to go in a bit more gently. Otherwise, the nugget would grow very quickly in the vertical direction, which we don't want. So we have to go lower current for longer time for resistance welding of stainless steels. And we allow more time for heat loss. So that's why the process seems a little bit more inefficient with stainless steel. In either case, we are finding that the heat used for fusion is only a small fraction of the heat input. Now, this is not uncommon compared to other processes or industrial applications where energy is used. A lot of times, your computer can get very hot when it's being used, and you're losing a lot of heat over there. Even incandescent light bulbs, which were invented by Edison, those light bulbs are also very poor efficiency. I believe they are close to 95% inefficient. That means if you install a light bulb which is 100 watts and it is actually consuming 100 watts of electrical energy, it is only creating 5 watts of light. The other 95 watts is actually converted to heat. And that is one of the reasons the incandescent light bulbs would be difficult to change when they are running for some time and they are very, very hot to handle. I hope you found this video to be interesting. Other useful resistance welding videos on my YouTube channel include resistance welding fundamentals, tempering of resistance welds, projection welding, power supply technologies, parallel gap welding, nugget formation in resistance welds, and types of bonds in resistance welds. I want to thank you for your time in watching this video and hope you found that interesting. As I mentioned, there are many other videos. I think this is going to be the 42nd video on my YouTube channel. So if you would like to learn more about welding, please do subscribe by clicking the subscribe button at the bottom left of your screen. So next time when I post a new video, it will directly show up in your feed. I want to thank you for your time again and wishing you the very best in trying to understand more about welding, and take care. Thank you.